Hello, welcome to this discussion. I'm Dr. Rosa Said Kandezi, and today we are going to talk about the arc flash hazard, its calculation, and the mitigation techniques that exist. And we are going to talk about those concepts based on the standard IEEE 1584. Now, for this discussion, let's begin with a fundamental question that what is IEEE 1584 and why does it matter? Now, this standard is actually a global standard for quantifying and mitigating the arc flash hazard. So it was first introduced in 2002, but the next version, which is 2018, actually marked as a turning point for arc flash safety. The reason for that, the importance of the 2018 version is that because it includes over like 1,800 full-scale laboratory arc flash tests, meaning it's not just a theoretical model, it's actually grounded in experimental data that are collected under the controlled but highly realistic conditions. Now, the first objective of IEEE 1584 is to basically quantify the arc flash hazard. That means using a consistent mathematical model to calculate how much incident energy could reach a worker during an arc flash event. So this energy is typically expressed in a calories per square centimeter, and it tells us how dangerous the exposure to the arc flash is. Now, for example, like we could have like 1.2 calorie per square centimeters, which is enough to cause a second-degree burn. Now, if we can quantify the energy, we can take meaningful kind of like steps to reduce that exposure and the consequence of the incident. Now, the second aspect is the IEEE 1584 actually helps us to make a risk-informed decision. Okay, so electrical safety is not just about rules, actually, like it's about understanding and understanding the magnitude of the risk and designing the system to manage that risk appropriately. Now, this standard actually supports this concept by enabling the engineers to model different scenarios and basically evaluate how factors like equipment configuration or fault current and clearing time can impact the workers' safety. Now, this standard also helps organization to meet the requirements of the regulatory agencies. Okay, in the US, like we have OSHA, or we have NFPA 70E in Canada. These standards actually all are mandated as arc flash risk assessment. And basically, the IEEE 1584 is the recognized method for performing those assessments. So it is the benchmark that regulators expect us to use for calculating the risk of an arc flash. Now, this standard also directly supports the selection of like appropriate personal protective equipment. We are going to call it PPE. Basically, by calculating the incident energy level at the worker's location, we can basically determine the minimum arc rating. So we could decide about the clothing, the gloves, the face shields, and other protections. Like if a calculated energy level is, for example, 8 calorie per square centimeters, then we have the category 2 PPE. So we have to like follow that category. and anything less would leave the workers actually exposed to a dangerous situation. We are going to talk about those limits and what we mean by category 2 in the upcoming slides. Now that we understand actually the purpose of this standard, let's turn our attention to where it applies. And just as importantly, where it does not. The IEEE 1584 is not a universal model. It was actually developed specifically for a certain class of electrical systems. So applying it outside this scope, this defined scope, would lead to a misleading or like an unsafe result. Now, let's walk through the key parameters that defines actually the applicability range of IEEE 1584. Now, one aspect is the voltage range. So IEEE 1584 is only valid for AC system, alternative current system, that are operating with a nominal voltage of 208 volt up to 15 kilovolt. Okay, so this is the range. Lower than that is lower than 208 volt is outside of the scope of this standard, and also the voltage higher than 15 kilovolt is also out of the scope of this standard. Now, this basically covers most of the system that we encounter, like low voltage switchgears or like a motor control center or panel boards, and even like medium voltage switchyards. These are the system that normally are in the scope of IEEE 1584. Now, next parameter that defines the scope is the system type. Okay, so IEEE 1584 is specifically designed for three-phase AC power system. That means a single-phase system is not in the scope of this standard, and also DC system also are excluded from this standard. So this is critically important because the physics of an arc flash in a DC system is fundamentally different. So all the methods for the calculation of the arc flash hazards or defining the categories or mitigation techniques, they don't work for the DC system because of that fundamental difference between the physics of these two arc flashes in DC and AC system. Now, frequency is also another aspect that defines this scope of this standard. So this model assumes that our nominal frequency in our system, the fundamental frequency in our system, is either 50 hertz or 60 hertz. Okay, which basically in a power system is it covers the vast majority of the commercial and industrial power system. However, we might have some system like in an aircraft equipment that works with 400 hertz frequency, or we would have some variable frequency system which has a wide harmonic contents or resonance circuit. These are not in the scope of this standard. Now, another factor is the geometrical configurations. So this actually relates to the physical configuration of our equipment. So, and this is a major enhancement that happened in 2018 revision. So this IEEE 1584 explicitly accounts for whether the arc is enclosed or in open air, and how the electrodes are oriented. So it could be vertical in a box, or vertical with barrier, or horizontal in a box, or vertical in open air, or horizontal in open air. So the configuration matters when we talk about this standard. So the geometrics actually significantly affect the directionality and the concentration of the arc energy, but in VCB, the vertical inbox compression energy is funneled directly outward toward the opening. Okay, in HCB, horizontal in the box, it's even more intense. So it hitting the worker directly. Okay, so we need to pay attention to those configurations. So these distinctions are not just theoretical or academic. These standards actually uses these different experimental correction factors for each of the configurations. So misdefining the geometry can result actually in inaccurate incident energy prediction. Now, we talked about the standard, but let's step back and basically define what is an arc flash. Now, an arc flash is not just a spark, okay? It's a violent, high energy event. So a rapid release of electrical energy that is caused by an unintentional short circuit, and it happens through the air. Okay, so basically it's a plasma explosion, and it can occur and happen in a fraction of a second, but it can release enough energy to melt steel or even vaporize the copper and cause permanent injury or death. So let's walk through the key physical phenomena that defines this arc flash. Now, one is the plasma formation. So basically, it all begins when air becomes ionized. So that is, it's basically its molecules get stripped of the electrons and become conductive. Now, normally air is a good insulator, but when the electrical field actually exceeds about like 30 kilowatts per centimeters, that air is gonna break down. So this breakdown initiates what is called a plasma channel. And that plasma is an extremely hot, highly conductive state of the matter. And basically, essentially, electrically charged gas. Plasma is electrically charged gas. Now, think of this like a certain, creating a lightning bolt inside your electrical device. Now, another concept that is important for defining the arc flash is the high temperature. Okay, so when we have the arc flash, when the arc flash actually forms, the temperature of the plasma skyrockets. So it could often reach like a 35,000 degrees of Fahrenheit. Okay, so which is hotter than the surface of the sun. Imagine that. Now, at this basically temperature, the copper would vaporize instantly, and the surrounding air rapidly would expand, and basically nearby surfaces that could include tools and the protective gear may ignite or even melt. So even a fraction of a second of exposure to this level of the temperature is enough to cause severe damages and severe burns, which is why the incident energy is a very critical metric in arc flash analysis. Now, another aspect is explosion. So when copper vaporizes, it expands by the factor nearly equal to 67,000 to 1. Okay, so it's a extreme expansion. Okay, so this sudden expansion acts like basically like a bomb going off inside your equipment. So that explosive pressure wave, which we call it normally arc blast, again talk about it in the future slide, can basically blow open panel doors or shatter the enclosures or through the workers across the room. Okay, so these spikes basically is powerful enough to cause secondary injuries, and even if the worker isn't burned, that blast could create dangerous consequence for our workers. Now, another aspect that we need to pay attention when we defining what is an arc flash is the thermal radiation. So we talked about the level of the temperature that happens in arc flash. So this level will actually create a radiant heat, which is an intense infrared and ultraviolet radiation. Okay, this is important. Even if you are not physically touched by an arc, the thermal radiation can burn your skin. Okay, and even ignite your clothing. So this radiant energy can also damage vision with the ultraviolet light, basically causing the flash blindness or retinal burns. It's similar to the welding arc flash exposure. Okay, so but it is stronger. Okay, now that we described what an arc flash is, we need to go a little bit deeper into the physics driving it. So basically understanding the cause and effect chain that happens behind an arc flash is not just going to help us to calculate the risk, but also design the systems that disrupt the chain before it completes. Okay, so let's walk through the four key physical stage of an arc flash event. When an insulation fails, basically, or a conductive path is introduced, the current jumps across the air gap. So the first condition necessary for an arc flash is the formation of the path for current through the air. So normally, as we said, air is a strong insulator, but sometimes we having a problem, we exceed a certain threshold for like a aging or moisture or contamination, or even the level of the voltage, or even when we could like drop a tool that would reduce that air gap and cause a short circuit. Okay, so when that path actually happens, even if it's momentary, current will jump across the air gap, especially when the voltage is sufficient enough and the path has a low enough impedance. Okay, so the electric field overcomes that air resistance and the arc initiates. So it's similar to lightning effect, and but but it's in our case it's happening inside our electrical equipment. Now, when that air becomes conductive, the currents begin to jump across. When the current begin to jump across that air gap, it rapidly ionizes the air molecule. So which means basically the electrons in the air molecules are stripped away. So it becomes a plasma, basically. Okay. This plasma is extremely conductive. Okay. Once it forms, it sustains itself because the current flow continuously provide the heat to further ionize the air. So at this point, you essentially create an electrically conductive flame between the conductors. So uh, this plasma bridge behaves like a low resistance wire. Okay. Uh, in numerical terms, the dielectric strength of dry air is about 30 kilovolt per centimeters, meaning if we have 1 centimeter of air gap, it could tolerate up to 30 kilovolts of voltage across that air gap. But once the local electric field exceeds the air, it cannot longer hold back the current. Now, rapid current flow, as we said, generates extreme heat in that plasma, which is basically the I squared R losses. This is like the same aspect of the power in the Ohm law and power losses in any type of resistance. Okay, now, as that current flows through that plasma, it introduces a heat by Joule heating, which is we could calculate that by the a specific equation. Sorry. That specific equation is Q equal to I squared times the resistance times the time. Okay, so here the I is the arc current, the R is the resistance of the plasma, and the T is actually the time duration of the arc existing in our equipment. Okay, so these formula give us the Q, which is the Joule heating uh, resulted by that arc flash. Now, even though that the resistance of the plasma is low, but the current is extremely high. Okay, so when we have like a very high current and we have like a square of that current uh, basically included in the how much joule of heating we could have, this is basically creates a massive heat. Okay, so temperature within the arc can, as we said, exceeds 35,000 degrees of Fahrenheit. And this is the main source of actually the incident thermal energy that we calculate during the arc flash analysis. And it's also what causes the PPE to ignite if it's not properly arc rate. Now, conductors like currents, okay, instantly vaporize in such a condition. So it's create, as we said, an expansion pressure that could exceed 10,000 psi. Okay, it is very high pressure. So let's put this into perspective. When a copper vaporizes, so it expands by the factor about 67,000 times. Okay, so that's like taking a grain of a sand, and turning it into a soccer ball in a blink. Okay, so this expansion, which is an instantaneous expansion, produces a shock wave, and which, as we said, the pressure of that shock waves would exceed 10,000 psi. This will blows apart the equipment enclosures, launches molten shrapnels, and can physically throw the workers through the room. And in many severe cases, these mechanical blacks actually cause more secondary injuries than the arc hits itself. Okay, so now, so far we've looked at what an arc flash is and the physics behind how it forms. Now we have to shift our focus to a more practical question, and it's what causes an arc flash events in the real world electrical system. Now, this understanding the causes actually allow us to move from a reaction to basically preventing the arc flash to happen. Now, arc flash can cause based on what three main categories of reason. One is human factors. The second one is equipment related causes, and the third one is the environmental condition. Now, let's go a little bit deeper into those categories. The human factor is by far the most common and most preventable actual category. So these arc flash incidents often happen not because of bad equipment, but because of the avoidable actions during the maintenance or testing or operation. Okay, so this is like when we talk about the accidental contact during the maintenance. This is a classic case where the technician tool or like body parts bridges two energized conductors or the conductor to the ground. Okay, this is a simple slip of like a screwdriver in a panel that can initiate that argument. Now, dropped tools also, like it's one of the human factors. A metallic tool that is dropped into an energized bus bar can short circuit the conductors in a millisecond kind of like time scale. We have another factor, which is inadequate PPE usage, which is like if we wear a non-arc rated clothing or omitting gloves, basically it means any exposure to the arc energy can result in a severe burn or even fatal injuries. Now, another aspect of human factor in arc flash event is when we have an unqualified personnel which having access to the energized equipment, and it's when the people without proper training or certification basically attempt to open energized enclosure and gears, which basically by that a risk rises exponentially. Okay, they may not follow the lockout or tagout procedures or understand the system's arc flash labeled it. Also, this means basically human error are often the weakest link in the safety chain. Okay, but it's actually easiest a factor that we could fix. Now, another factor, as we mentioned, is the equipment factor. Now, let's talk about that and talk about the most common contributors in this category of the equipment factors for arc flash. One is the insulation failure. So we know that over time we have aging in our system, and the electrical insulation basically get weakened due to heat or moisture or contamination. So once that insulation strengths basically decrease, we could have a high risk of arc flash in our system. Now, another factor is loose terminations. So if we have like a slightly loose log or connector, which normally you may not consider it as a very big deal, but it causes some localized heat. Okay, there is a specific standard for temperature rise for electrical equipment, especially power equipment. And if you look at the testing result for that standard, like the experimental test, you can see that a slight losing kind of like connectors significantly increases the temperature rise under the nominal operational condition in that equipment. So when we have that localized heating, which can melt the insulations or deform the terminals, it could cause like a face-to-face or face-to-ground faults, which can initiate an arc flash. Now, another factor is like a dust or dirt or corrosion buildup. So these are all conductive or semiconductive contaminants. So over time, they can form an unintentional breach between the conductor inside our system. Now, we have also a rodent or pest intrusion, which sounds a little bit awkward and unusual, but is quite common in outdoor or poorly sealed equipment. So in a small rodent breeding terminals can cause a massive arc flash. So both from the arc and the resulting plasma created from that creature's body vaporizing could have like a severe risk as a result. So that's basically why routine maintenance or infrared inspections or torque checks and proper sealing is very essential when we talk about the arc flash events. Now, we said that the environmental condition also is a factor that could cause an arc flash. So the most critical ones in the environmental conditioning is that when we have a condensation or high humidity. Okay, so basically we know that the moisture reduces the surface resistance in the insulation material and can basically form a conductive films on the surface of those insulation material. Okay, this is especially dangerous in coastal or unconditioned environments. Okay, so we also could have vibration, which the high level of the vibration, like in the motors or compressors, basically can cause the connectors to loosen over the time. And we talked about what will be the effect of that earlier. Now, we could have voltage surges or transient fault. This is also considered as an environmental condition for our equipment. So events like lightning strikes or capacitor switching or a motor starting can induce transient overvoltages that could exceed that dielectric withstand of the air that we talked about, which initiating an arc even in like a well-maintained systems. Now that we discussed what causes an arc flash, we also need to address a more kind of like sobering question, which is what happens when an arc flash actually occurs or happens. Now, the consequences are often catastrophic, not just for the worker, but also for the equipment and the facility. Okay, so that arc flash is not just an inconvenience or a minor operational event. So it is a life-threatening explosion. Okay, so we categorize the consequences into four primary impact areas. One is the thermal injuries. Okay, that arc flash, as we said, can generate the heat like up to 35,000 degrees of Fahrenheit. Okay, so this heat is released as a thermal radiation. Okay, primarily like infrared or ultraviolet kind of like radiation. Okay, and can instantly ignite the clothing or cause steam burns. Okay, even if you don't have a direct contact to that arc flash. So here's some key points data that you have to remember. So a secondary burn can happen at just 1.2 calorie per centimeters of incident energy. We are going to see that this is the lowest category of arc flash. Okay, so at the level when we have more incident energy, like 8 to 10 calorie per centimeters per square centimeters, we could have third degree burns, okay, which is almost certain that that would happen. And basically the survival of the workers becomes uncertain, okay, if we don't have immediate care. Now, let me give you an idea of the scale. Okay, so a stove top might emit 0.1 calorie per square centimeter per second. Okay, 0.1. The minimum arc flash is 1.2 calorie per square centimeter, almost 12 times than a stove top. A moderate arc flash can release like around 20 calories per square centimeter in a fraction of a second. Well, actually, it would happen like in 0.1 seconds. Okay, that's like thousands of times more intense than standing next to a red hot burner. This is why incident energy calculation and the PPE rating actually matter. Okay, so the human skin can only absorb so much energy before irreversible damage begins. Now, another consequence of that arc flash is the arc blast, the pressure that happened when an arc flash ignites in our system. Now, the arc flash itself often are associated with heat, okay, and the mechanical force, which we call it arc blast, is just as dangerous and is one of the consequences of that arc flash. So we said when a copper vaporizes during the arc flash, it expands 67,000 times its solid volume. You can imagine this rapid expansion would generate a very strong shock wave that, as we mentioned before, can produce over 10,000 psi of pressure. Now, this level of pressure can basically blow open the panel doors or rupture the eardrums. Okay, this is from sound level exceeding like 140 decibel, or through the technician several feet, which cause severe trauma, falls, or even fatal impacts. So even if the worker is outside the thermal impact zone, they can still suffer secondary injuries from that arc blast, from that shock wave that happens after the arc incident. Now, another consequence would be the visual effects. That arc doesn't just emit heat, as we said, it also release intensive UV radiation, ultraviolet radiation, and visible lights, which both of them can be dangerous for the eyes. Uh, Short-term effects could include like flash blindness, which is temporary, photokeratitis, which is like a sunburn of the retina, and retinal burns, which is permanent damage. Okay, even a brief glance of arc happen to any human eyes, particularly during the switching or racking operation. This can cause damages if but we don't have proper eye and face protection. Now, another consequence, which you can imagine, is equipment damage. So arc flash events normally result in a severe equipment destruction. As we said, it's gonna vaporize the conductors, okay, and the bus bars inside our equipment. It could melt or deform the panel enclosures. The insulation is gonna break down across multiple phases, and we are gonna have welded conductors and the breakers after an arc flash. Now, we mentioned arc flash and arc blast as about two different type of consequence when we talked about the consequences of the arc flash. Now, we are going to talk about the differences so we know how to distinguish and what are the arc flash and arc blast. Now, an arc flash is the release of radiant thermal energy during the electrical arc. So it's primarily caused by ionizing plasma, which is formed between the conductors under fall condition. The primary hazard for those arc flash is extreme heat, radiant infrared, and UV energy, molten metal spray. Okay, and these hazards actually lead to severe burns or ignition of non-arc-rated clothing or thermal injuries to the eyes and face. Okay, the affected area by the arc flash is typically directional, so it travels outward from the arc source, specifically in enclosed gear like panel boards or switchgears. This energy flows a conical or fan-shaped path outward from the electrodes. Okay, we could have several mitigation strategy for arc flash, which the most effective one are like use of arc rated PPE for safety of our workers, or accurate arc flash labeling, or proper working distance, and engineering design, proper engineering design like current limiting devices or reduced fault clearing times. Now, on the other hand, arc blast refers to the pressure wave caused by the rapid vaporization of the conductors and the superheating of the surrounding air. So it's a shock wave. Okay. It is driven by the mechanical expansion of the plasma and the metal vapor is not a thermal radiation. And the blast can cause like blunt force trauma, hearing damages, or secondary injuries, which basically when it could throw the people several feet away. So you can imagine there is going to be secondary damages to the person. As we said, panel doors can be blown open and workers can be knocked backward or into the equipment. These could have like a concussions, cause concussions or fractures, or worse. Now, arc blast energy is generally radiated outward in all directions. Okay, this the intensity is highest near the arc origin, but the shock wave propagates broadly, which makes proximity especially dangerous. Okay, so we have several mitigation strategy for arc blast. One is an arc resistance switchgear that basically channels pressure upward. Okay, so it's guide the blast to a safe, direction, or physical barriers or blast shields inside our equipment, or remote operation tools, so we don't have a direct maintenance workers working on the equipment, or a strict boundary enforcement. So, in other words, the engineering controls basically are the primary defense when we talk about the arc blast. Now, let's talk about some real-world case studies of those arc flash events. Now, in this slide, we're gonna walk through two actual incidents that arc flash events happened, and we are gonna analyze it step by step, each of them step by step. So we are gonna talk about the maintenance-induced arc flash and a bus fault triggered by the environmental intrusion. Now, the first case study is the scenario is a technician was performing maintenance on a 480 volts motor control center. During the process, he accidentally dropped a screwdriver, which fell across two energized phase conductor, causing a phase-to-phase arc. Okay, this kind of scenario is unfortunately very common and normally happen during like breaker testing or voltage checking or component replacement. Okay, now let's break it down step by step. Now, the MCC was energized and under normal operating load. We didn't have any lockout or tag out in our system. The technician was working barehanded in the energized area, and the PPE included a standard cotton shirt and non-arc rated gloves should be worn. Okay, the screwdriver was a standard metallic hand tool. This condition violates the key NFPA 70E guidelines, which states that energized work requires first justify energized work permit. So the personnel, the maintenance worker should be certified. There should be an arc rated clothing suitable for that specific incident energy level. and we should have proper insulated tools and the barriers. So we see that we missed several aspects of the guideline. Now, when the screwdriver slipped and dropped vertically, it bridged two-phase buses. So it's immediate face-to-face fault. And basically it caused an arc flash instantly, forming a plasma channel and vaporizing the metal and at the contact points. Now, based on IEEE 1584 and its calculations, the incident energy at the worker's chest was approximately 6.3 calorie per square centimeter at an like 18-inch distance. Okay, this is well above that 1.2 calorie per centimeter threshold for the second-degree burn, and within the range of category 2 arc-rated PPE. We are going to see those definitions later on. Now, the immediate outcome is going to be the technician would suffer second-degree burns on both hands, okay, and forearms. The cotton shirts ignites partially, okay, which increase the thermal injuries. The gloves would melt it, basically offering a no arc protection, and he was basically that worker would be hospitalized for treatment and miss several weeks of work. Now, when we talk about the regulatory and legal impacts, that employer will be cited by OSHA for failure to enforce arc flash safety policies. Okay, there was no arc flash risk assessment or labeling, okay, performed for that MCC. The PPE requirements were not communicated to the workers, and there was no documented training found for that involved employee. Now, even what it tells us, even a common tools like screwdrivers can become very fatal, can become fatal hazards when we talk about an energized environment. So maintenance on energized system should always be justified, okay? And they should always perform only if the de-energization is infeasible. We should have arc-rated PPE that has to match the calculated incident energy, and all the employers should have proper training, documentation, and clear labeling per IEEE 1584 and NFPA 70. Now, we have another case study that happened actually, and it was an outdoor high voltage switchgear that experienced an arc flash after its door was blown open during a storm. So rainwater entered the energized compartment and causes a face to the ground arc fault. And basically what happened before the event was the cabinet was located in the outdoor switchyard. The operating voltage for that specific configuration was 4.16 kilovolt. And the switchgear was not properly sealed, so the door latches were corroded and failed during the storm. So no real-time monitoring also was installed to catch that failure, and the worker was nearby but outside of the arc flash boundary. So let's see in that condition what's going to happen. Now, we said the high winds caused the failure in the panel door, and the rainwater get into the system, which creates a breach for the area. Because of that, an arc initiation happened, and it's happened vertically inside the enclosure. Okay, so it is the configuration, as we said, the configuration is vertical conductor in a box, VCB configuration in IEEE 1584. The arc propagates through the interior and vaporize portion of the bus bar and triggering the protective device operation. Now, in that case study, the calculated incident energy was more than 20 calorie per square centimeter, which is classified as category 3 to 4 based on the working distance. Now, when that happened, the immediate outcome was no injury happened to the technician because it was outside of the arc flash boundary. Okay, and the switchgear could sustain the extensive internal damage. Okay, which is vaporized copper, destroyed insulation, and deformed enclosure panel. And the arc was extinguished after the upstream differential relay tripped the brake. Now, after the incident in that case study, a full investigation basically revealed a poor preventive maintenance. There is no weather swing. Okay, the AFB and incident energy were never labeled on the panel. The fault led to a day-long outage, which affected the nearby industrial customer. And the total repair on that specific case exceeds the cost. The cost exceeds the $250,000. Now, from that incident, we are going to learn. This is the lesson learned, that environmental intrusion must be treated as serious as arc risk. Okay, so equipment doors must be mechanically secure and weather tight. Okay, so must be regularly inspected. The remote operation or weather related enclosure can prevent such incidents. And arc flash boundaries must be clearly marked, and no work should be done within those zones without a PPE and appropriate protection. Now, we several times mentioned the incident energy as one of the key concepts. Let's talk about it in more detail. Basically, at the core of everything we do in arc flash analysis, okay, there is one key quantity that drives everything, and it's incident energy. Okay, so let's see what is actually incident energy and why is it so critical when we talk about the IEEE 1584 context. The definition is that incident energy is the amount of thermal energy that a worker could be exposed to on their body surface at a specified working distance from an arc flash fault. Okay. In practical terms, it's measures of how much heat is delivered to the worker's skin or the PPE that the worker wear in the events of an arc flash. Now, it counts for the arc currents, the duration of the arc, the distance from the arc, the distance of the worker from the arc, and the configuration of the and geometry of the enclosure. So all of these are important when we talk about the calculating the incident energy. And it calls incident energy because it is energy incident upon the surface. Okay, so this value is the main input that we want to determine the arc flash boundary or the PPE category or equipment labeling and overall risk level. Now, we said that the unit for this quantity is calories per square centimeters. This is a thermal energy unit. It's not electrical, okay? And it directly relates to how much heat your skin or clothing will absorb during the arc flash in a certain distance. Now, the IEEE 1584 defines a few critical thresholds that you need to memorize and you pay attention. The first threshold is when our incident energy is 1.2 calorie per square centimeters, okay, which is the threshold for second degree burns. We have 1.2 up to 4 calorie per square centimeter, which is minimum for the category 1 PPE, okay, and it is like a low incident energy, okay, but needs an arc rated protection, okay. We have more than 4 up to 8 calorie per square centimeters, which is a moderate risk level. It has a higher energy fault, okay, and it could be often seen in panels and MCCs that works like in 480 volt nominal voltage. We have more than several other categories, more than 8, less than 25 calories per square centimeter, which is category 3. It is a high risk of the severe burns or injuries. The category 4 is more than 25, less than 40, which is a very high risk of catastrophic injuries. Okay, and if we have more than 40 calorie per square centimeters, it's considered very dangerous. It's considered as a non-survivable because of the pressure and thermal hazard. There is no safe PPE, so the work under those kind of like incident energy level should be done in a de-energized state. There is no way that you can protect yourself against that level of incident energy levels. Now, based on that incident energy race, which is a critical risk metric for arc flash, okay, we can define arc flash boundary, or as we call it, AFB. So let's say if incident energy tell us how much heat a worker might absorb, okay, then the arc flash boundary tells us how far away a worker must stand so we could avoid serious injuries. The definition of the arc flash boundary is that the distance from a potential arc source at which the incidence energy drops to 1.2 calorie per square centimeters. Why this amount? Because that's the industry acceptable threshold for onset of a second degree burn as defined in the standard in the table that we reviewed in previous slide. Now, if you're closer than that distance, the arc flash boundary, you are at risk of injury from heat and molten metal. And if you're outside of that boundary, the thermal explosion will be below the burn threshold. Okay, so let me put it in a simple terms. Inside the AFB, workers must wear a full arc rated PPE. Outside of that AFB, PPE might not be required depending on the task and other risks. Okay, so it doesn't mean that there is no danger outside of the boundary. It just means that the thermal energy dropped below the injury threshold. Okay, so we also would have on that boundary outside of that boundary, we still have arc blast or a sharpnel or a sound may still be causing damages to the work. Now, how AFB is calculated basically. The IEEE 1584 provides a precise experimental equation to calculate the arc flash boundary. It derives from the extensive arc testing in real equipment and has been statistically fitted to match the observed energy profiles. So the formula for AFB is that AFB is equal to the D times square root of IE incident energy over 1.2. Okay, and this is going to be our boundary. Now, that AFB, as we said, is the arc flash boundary. That D is the working distance. This is the working distance. And the IE is the incident energy that we have for our specific situation. Okay, at that specific distance. And 1.2, as you can imagine, is that threshold, is the burn threshold. Now, these equations assumes that there is an inverse square energy decay based on the distance. Okay, so it is corrected for enclosure effects, electrode configuration, and plasma expansion geometry. So, like for example, if incident energy is 9.6 calorie per square centimeter at 18 inches. Okay, so let's say we have IE equal to 9.6, okay, at 18 inches. The AFB for this situation would be the AFB would be 18, this D is in inch, times 9.6 over 1.2 square root of that fraction, which basically means it's about, if you do the calculation, it's about 50.9 inches. So this is our boundary, arc flash boundary. Outside of this distance, we are within the burn-in threshold. Inside of this distance, closer to this amount of distance to the arc flash source, you need to have the properly rated PPE for those situations. Now, AFB is not just a number, okay, that you mention on a label. It is a critical quantity when you want to look plan a job or design a facility. So if the task brings them being the workers inside the AFB, they have to wear flame resistance clothing or arc rated gloves or face shield, okay, or hearing protection and safety glasses. For engineers and managers, that AFB means design of the equipment layout or placement of the warning signs, okay, or designing the PPE policies and the training contents, or the policies for safe working distances. Okay, so there are some misconceptions about the AFB. Let's mention those. Let's clear up those common misunderstandings. AFB is not the same as working distance. Working distance is assumed chest to source distance. Okay, AFB is computed as radial distance where the incident energy will be 1.2 calorie per square centimeter. So AFP is not a fixed number. It changes when we have a change in a system voltage or fault current or arc duration or equipment type or even enclosure size and geometry. So AFB also does not account for arc class. Please make sure you pay attention to that. This does not account for arc class. That arc class requires separate class zone analysis. Okay, so two different things. Arc flash boundary is only for the thermal radiated safety. Okay, class is something else. You need to consider that individual. Now, at this point, we explored two foundational ideas in arc flash. One was the incident energy, which is the thermal exposure from an arc, and arc flash boundary, which is the distance where the exposure falls below the injury threshold. Now, let's talk about the working distance. We mentioned that that is different from arc flash boundary. Let's talk about it. Now, this is one of the most influential inputs in IEEE 1584. Okay. And often is misunderstood or applied inconsistently with this standard. So, what is actually working distance? Let's talk about it. Working distance is defined as the distance from the prospective arc source to the worker's chest or face. Okay, the part of the body most likely to be exposed to an incident injury during the fault. Okay, now, this distance is not a guess. It's an assumed fixed geometry used to calculate how much radiant heat will reach the body in the arc flash scenario. So the closer you are to the arc source, the higher the incident energy. The farther away you are, the safer you are. So this concept is similar to standing near a bonfire. So as you move away, you feel less heat because thermal radiation dissipates with the distance. Okay, so why this working distance matters and is important? Because it directly influences the calculated incident energy at the worker's location. We already said when you want to talk about the incident energy, there is always a distance that helps us to calculate that, i.e. it is required arc rating, it influences the required arc rating of the PPE, okay? And it influences the computed arc flash boundary. Okay, so in fact, for a given system, doubling the working distance can result in cut the incident energy by a factor of 4. Okay, depending on the enclosure type. Okay, so choosing the right working distance is not just about the math, it's about modeling realistic human exposure. Now, there are some standard working distances by equipment type, which IEEE 1584 provides a typical working distance based on the equipment being assessed. Let's break it down by the voltage class. So we have a low voltage switchgears, which is 600 volt and below. Okay. Typical working distance is 18 inches, okay, which is about 455 millimeter. Okay, it is the common equipment are MCCs, the motor control centers, or panel board or switchboard. Okay, so at 18 inches, workers often interact with those equipments, with the breakers or terminal or energized bus bars. Okay, it could happen during testing or troubleshooting. So at this distance, even moderate fault current can produce incident energy that exceeds like 10 to 20 calories per square meters, which requires a category 3 or 5 PPE. Okay, if the workers get closer, for example, let's say 12 inch, the incident energy can double or triple. Now, we have another category of the equipment, which is the medium voltage switchgears that have like a 2.3 kilovolt to 15 kilovolt of the operational voltage, nominal voltage. The typical working distance on those equipment is 24 inches, which is about 610 millimeters. They are like indoor medium voltage switchgears or circuit breakers or metal clad gears. This distance reflects like for the larger cabinet depth and increased standoff. And we talk about the operation and maintenance. And when the work distance increased from 18 inch to 24 inch, the incident energy drops significantly. Okay, possibly enough to reduce the PPE category. But still, due to the higher arc energy and longer clearing time, when we talk about the medium voltage, PPE category normally remain high even at 24 inches. So that doesn't mean because you have 24 inches working distance, then you have to be you have to lower the safety criteria. You still have to calculate the IE and the AFB, and based on the IE, you choose the proper PPE category. Now, we also could have outdoor substations. Typical working distance on outdoor substation is 36 inch, which is about 910 millimeter. Okay, so it is normally like outdoor switch yards or pole mounted disconnects or edge switch terminals. So it allows a greater physical clearance, and the arc energy tends to dissipate in all directions. So especially when we have like a vertical open air configurations, the result is calculated incident energy are often much lower, and in some cases, arc rated PPE may not be required. Okay, when you're working beyond the arc flash bond. Now, to clarify 2 points that often confuse practitioners, we have to mention those. Working distance is an input, not a result. When performing the arc flash analysis, working distance is an assumed input, not an output. Remember the arc flash boundary. That distance, that D was an input to that arc flash boundary. Okay, and you may select, you have to select on that based on equipment design or access point or typical worker posture during energized test. Okay, if you underestimate the working distance, the calculated incident energy will be artificially high. Okay, and if you overestimate that, the result will be dangerously low. So you need to pay attention to that. Now, that's why IEEE 1584 actually recommends using the standardized working distance unless there is an actual measurement or safety policy that is dictated otherwise. Now, again, working distance is not equal to arc flash boundary. Okay, it is important to distinguish those two concepts. Now, working distance is the assumed position of the worker relative to the arc source. Arc flash boundary is the computed safe perimeter where incident energy becomes 1.2 calorie per square meters. So as we said, working distance is an input, AFB as the output of the incident energy analysis. Now, we said we have several electrode configuration that could affect the flash risk modeling. This is the physical arrangement of the conductor, okay, during the arc incident. Now, IEEE 1584 defines the electrode configuration as is not just the afterthought. It is a required input to calculate both incident energy and the arc flash boundary. Okay, so let's explore the electrode configuration means and different types that are defined in IEEE 1584. Now, electrode configuration refers to the orientation and a spatial arrangement of the conductor within the equipment enclosure. Okay, basically it defines how the arc plasma expands or how much of the energy is directed toward the workers and or how it interacts with enclosure walls. Okay, so in simple terms, whether the electrode is horizontal or vertical, okay, or they are inside the box or in open air, or their barriers alter the arc's expansion path, all these define that configuration, different configuration. Now, we have vertical open air configuration, which electrodes orientation are vertical. The environmental is open air, so there is no enclosure. Okay, and the rated energy level is normally 40. So this is the lowest severity of configuration because the arc expands freely in all directions. It's normally common in overhead transmission systems or outdoor substations or open terminal disconnects. And the lack of enclosure walls means minimal energy reflection. And so the radiant energy dissipates quickly. Now, workers at the ground level typically experience lower incident energy, but the arc flash pressure in the line of sight risk still remain the same. We have horizontal open air. Orientation is horizontal, environment is open air, no enclosure, and the relative energy level is 55. Now, here the arc forms between the horizontal conductors. Compared to the VOA, the vertical open air configuration, this configuration basically directs more plasma and thermal radiation often toward the workers. Okay, this happened like in outdoor bus bars or horizontal open disconnect switches. Still lower energy than in closed system, but more directional hazard than the vertical open air. Now, we have vertical conductor in the box. The orientation is vertical. We have an enclosure and the conductors are inside the enclosure. The relative energy level is considered 60 in the standards IEEE 1588. This one is the most common configuration when we talk about the real world low voltage equipment like MCCs, panel boards, or switchboards. Okay, the arc tends to shoot out of the closure opening, which basically means toward the worker's face or during the maintenance. Okay, so Enclosure walls reflect and channel the energy, okay, which intensifies the blast forward. We have medium severity, but high worker exposure. So full PPE and face protection is mandated in this configuration. We could have vertical conductor in a box with barriers, VCBB. Orientation is vertical. The conductors are in the box with a vertical barrier or phase separation. The relative energy level is considered 75, and this configuration normally happens when we have like a metal enclosed medium voltage switchgear or ring main units or gear with the internal insulating barriers. Okay, so these barriers may cause arc reflection and redirection, so creating a complex plasma flow and a concentrated actually energy path. So these barriers may seem safer, but they can focus the arc energy. So they could create a higher localized incident energy. So pay attention to that when you work with these kind of devices. We have another type of configuration, which is the horizontal conductor in box. The orientation, as you see, is horizontal. The conductors are fully enclosed inside our equipment. And the level of the relative energy level is 85, which is the highest level. This is the most severe of all the standard configurations because the arc plasma moves horizontally toward the front opening, which is exactly where the worker is standing. Enclosure walls reflect the energy directly toward the operator, okay, with a minimal loss to side walls or rear surfaces. And it normally, this configuration is using bus stocked enclosures or horizontal disconnect compartments or horizontal cable terminations inside the gear. So this is the worst case geometry. And you have to always expect high incident energy and consider remote operation or arc resistance gear. Now, let's talk about the IEEE calculation models. This is where the IEEE actually calculation model comes in. This model is practical, meaning is not purely theoretical. So it is built on over like 1,800 laboratory tests involving various equipment types and conductor geometry or enclosure dimension and fault conditions. The equation in the model are statistically derived and curve fits that allow us to estimate real-world arc flash with high confidence. Now, let's break it down as a step by a step through the full modeling procedures and apply it to a practical example. Now, the step one is to collect the input data. So before you can calculate anything, you must define the system parameters precisely. And you need, for that, you need one system voltage. Okay, this is operational voltage. You need available voltage fault current. Okay, which is short circuit current in kiloamp. Okay, the electrode configuration, you already talked about that. You have to know what type of configuration you have, VCB, HOA, HCB. We talked about that in previous slide. We have to know the conductor gap, which is the spacing between the conductors or from the face to the ground, and it's in millimeter. We have the enclosure dimensions, like width, height, and depth in millimeter. We have working distance, which is the typical face to arc distance or chest to arc distance It could be 18-inch, 24-inch, or 36-inch. And we have to know protective device clearing time, which is the duration of the arc in seconds. Okay, so these values must be measured or calculated using validated fault analysis tools like ETAP or Easy Power or SKM Power Tools. Now, when you have your data, you need to calculate arcing current. So IEEE defines a separate equation for normalizing the input based on the voltage gap and configuration, and predicting the arcing current under two conditions, like the standard arcing current or low arcing current. Now, the general form actually looks, let me write it down. Sorry, why is doing it? Okay, sorry for the interruption. The general form of the equation is actually looks like a log of 10 of the current of the arc should be equal to K1 plus K2 times the log of the current BF, this is log 10, plus K3 log of G plus all the way through the system. Now, K1, K2, and all the way to the all these coefficients are vary based on the electrode configuration or enclosure size. These equations are built into the commercial software, so but you must choose the correct configuration code. So you don't need to like actually know these coefficients. You just need to in the software you choose correct configuration, and they already know those numbers based on their standard. Now, next step is to determine the arc duration. So this is a clearing time of the upstream protective device. It could be a breaker or a fuse. So you can find this by running a time current coordination study, or like identifying the time at which the arcing current interacts the TCC curves. Okay, so you have to use the conservative estimates. Always choose the longer of the two duration, one based on a standard arc current, and another one is minimum arc current. Whichever is the longer this duration for the clearing the fault, you need to consider that. After that, you will calculate the incident energy level. Okay, the formula for incident energy level is IE is equal to C times C. Sorry, C times the arc current over V to the power of X to the power of Y times the time duration of the arc. Now, let's see what is IE is the incident energy, which is in a calorie per square meters. C, X, and Y are practical drive constants, so they are defined in the standards. The arc current is in the name is the current of the arc. The D is the working distance, which is in a millimeter, and the arc T, the time of arc, is the duration in seconds where the arc exists until protection would clear out. Now, IEEE provides the correction factor for enclosure size and arc directionality or conductor gap. So you need to use validated software and handle this, but the understanding of the math is essential. Now, when you have the incident energy, you calculate the arc flash boundary. We already gone through that, how we could calculate the arc flash boundary. Let's go over one example to make sure we understand this model. Let's say we have a case that our voltage, our nominal voltage, is 480 volt. Okay, our available fault current IBF is 25 kiloamp. Okay, our configuration is VCB, vertical conductor in a box. Our conductor gaps, that G here, our conductor gaps is 32 millimeters G. Okay, and the enclosure dimension, our enclosure dimension is, like, for example, 508 millimeter multiplied by 508 millimeter multiplied by 406 millimeter. So with height and depth. Okay, we have a working distance equal to 18 inches. Okay, and the clearing time, the time of the arc is 0.2 seconds. Now, let's use our like a software or IEEE spreadsheet tools to run the calculation model. Now, we have those input values. We are going to input that into the arc flash calculator. The first step is to select the right configuration. So our configuration is VCB. And then to calculate the arcing current. For this specific situation, our arcing current, the I arc standard, if you calculate that, will be the formula is in the standard, will be 18.6 kiloamp, and the I arc mean, the minimum arc current would be 14.9 kiloamp. Okay, and we have the arc duration is 0.2 second. So based on that, you can calculate the IE. You have this formula. You can calculate the IE, and it will be, if you run the formulation, IE that you have will be around 9.3 calorie per square centimeters. The distance is important at the 18-inch distance. And when you have your IE, you can use the AFB formula that we went through before, the AFB. And if you go through that formula, you will find that your AFB is going to be 15 inches. Now, so when you do this calculation, these are the most important part. You have your incident energy and you have your arc flash boundary. Okay, because of your incident energy, based on the categories that defines in IEEE 1584, this means you have the PPE category 2 or 3. Okay, it depends on your policy. And your label must include the voltage. This is your label. Must include the voltage, the incident energy, the AFB, the working distance, okay, and the PPE level. So these are the most important that you need to like consider. Now, we walk through the mathematical structure of that arc flash modeling defined by IEEE 1584. Let's talk about how this model is implemented in practice. Now, for most engineers, these complex equations aren't solved manually. So they normally use arc flash calculation, typically performed using like a dedicated power system analysis software. Now, using a software doesn't eliminate the responsibility. You still need to like have like engineering judgment and data integrity and a firm understanding of how the model works behind the interface. Okay, now let's talk about that. Now we have two main categories of tools within this standard. One is commercial software platforms. These are like industry standard tools that utility or consultants or engineers use for arc flash analysis. For example, it's going to be like SKM Power Tool for Windows or ETAP or Easy Power Arc Flash Suite, sorry, and or CYME Power Engineering Software. All these tools include IEEE calculation engine. There are built-in equipment libraries. So, and they have fault current analysis. They have time current coordination. They have one-line diagram interfaces and arc flash label generation. So they are very good for automating or like using the software instead of the manually handling the calculation model. They also provide configuration option. We said this is important, so you can choose the electrode orientation and you can choose the enclosure dimension. You can enter that. You can enter the conductor gap or working distance and arc duration based on the relay and breaker clearing time. So these platforms are fully validated against the IEEE 1584, which make them very suitable for compliance grade studies. Now, this is one of the examples. You could see you can have like a configuration. There is like an enclosure dimension. We have our fault method. We have our nominal values. The bolted fault, you see IDF. We have the voltage. We have the G conductor gap. We have the D working distance. All these are going to happen there. Based on these configuration, it automatically calculate the arcing current, the IE, the incident energy, and the AFP arc flash boundary. And basically, it's a very, and it gives you actually the arc flash boundaries. You see how efficient is that when we talk about this software system. Now, these IEEE methods provides Excel-based arc flash spreadsheets, okay, which is for educational use only. It allows you to input parameters manually and select the configuration codes, see how the raw equation works, and understand how different variables affect the outcome. Now, when you want to like use the best software and having the best practice using those software, you need to pay attention to several aspects. One is the model of the power system. So you have to build the one-line diagram of the electrical system inside the software, which includes all the buses, breakers, loads, and transformers. or source data like utility short circuit capacity or generator specifications, and you have to have like accurate cable and impedance data. Okay, so after that, you perform a short circuit analysis. So you run a three-phase bolted fault current study, which basically IEEE 1584 requires a minimum and maximum available fault current at each bus where energized work may happen. Okay, so this forms basically a starting point for our current prediction. Then for each bus or equipment type, we assign a voltage level, electrical configuration, the conductor gap, the enclosure dimension, the working distance, and the clearing time. Okay, so most of the software tools allow you to create templates for different type of equipment. So it's not gonna be very kind of a complex situation. After that, we run arc flash study. Okay, so the software will calculate the arcing current, extract the clearing time, okay, compute the incident energy. It defines the arc flash boundary and assign the PPE category for those specific estimation. Now, you can also, as we said, generate the arc flash label, okay? And we already said what are the information needed for that label, okay? But pay attention, even that though that the software handles the mass, you are responsible for the validity of the input and the results. So the IEEE recommends use of conservative values, okay, when we talk about the fault current and clearing time. You have to validate manufacturer data, okay, for the conductors or gaps and the breakers. There might be errors when we talk about the specification via versus the real dimension values. You have to ensure electrodes configuration match the actual geometry, so check that. It's very important. And you have to recalculate arc flash risk every 3 to 5 years. Okay, so ensure that your software version is updated. So it could include the latest version of the IEEE 1584 or the configuration specific arcing current models or enhanced enclosure correction factors. Now, we mentioned several types that each of the incident errors and distance would create some PPE categories. Okay, so what are those categories? We have 4 categories in the system for arc rating, the incident energy. This is basically how we protect the workers from the incidents. Now, the category 1 is when the arc rating is at a minimum 4 calorie per square centimeters. Okay, typical clothing is arc rated long sleeves shirt and pants. It also includes safety glasses and hard hats with arc rated face shield or goggles. Okay, so it is normally suitable for tasks with low fault current or fast breaker clearing time or high working distances. Now we have category 2, sorry, which is the arc rating of minimum 8 calories per square meters. Now, there is an additional clothing added to that category 1, which is arc rated hood, okay, and a heavier arc rated shirt, pants, or layered FR system. Okay, so this is the most common PPE level in low voltage gears like panel boards and MCCs at 480 volt. Okay. There is a category 3, which is the minimum arc rating of 25 calories per square centimeters. We should have full arc rated suits, like jackets and pants. Okay. Arc rated hood with the face shield. We have to have gloves, hearing protection, and safety boots. Okay, so This is normally used in a system with higher available fault current or longer clearing times, or horizontal inbox configuration. We said that's the worst case of a configuration, which is basically produce greater incident energy. Category 4, the last category, is when we have arc rating of minimum 40 calorie per square centimeters. Okay, we should have a heavier arc suits or multi-layer system for our protection, and we have to have a complete body enclosure, including the face, necks, and hands. It is for extreme cases like typically medium voltage switchgears or older breakers with slower clearing or where the working distance is limited. So you have to be very close to this distance, way closer than the arc flash boundary. Okay. Now let's talk about the label. We mentioned that label. The label that is defined by the standard are more than just a sticker. They are life-saving communication. Okay, so the regulatory for the label is not optional. It is mandated. Okay, and basically the clause in the standards requires that the electrical equipment such as switchboard, panel board, industrial control panels, meter socket enclosure, and motor control centers that are likely to require examination or adjustment or servicing or maintenance while energized shall be field marketed with a label. And that label must be updated when we have a new arc flash study, or we have a system modification that changes the fault current or the protection settings, or at least every 5 years, whichever is the smallest time. Okay, so as part of the documented reassessment. Now we have several aspects that we have to include in the label. One is the nominal system voltage. Another one is the arc flash boundary. We have to mention that. We have to mention one of the following categories. One is the available incident energy and the working distance, okay, or the PPE category. So either you can have both of them, but either you can have the PPE category to tell the workers, okay, what to do, or you have to have the incident energy and the working distance, okay, so they can realize what level of the protection they need. Now, understanding that label, okay, is very important. Let's say, imagine a worker approaches a panel with a certain label, okay, so basically that helps them to realize that they are dealing with a system that may deliver a certain amount of thermal energy. That label tells them what to wear to protect themselves, and they tell them they have to stay outside of a certain boundary unless they are properly protected. Okay, and it tells them that they must confirm that the label data is within the 5-year update window. Now that we discussed the arc flash, there are several mitigation technology that we could use. One is the elimination, which is de-energizing the equipment before performing the work. That's the basic one. We could have substitution, so replace the task with a lower risk alternative like a remote racking system. Or we could modify the system design with arc resistant switchgears or current limiting devices, okay, or differential protection to reduce the arc time. We could implement some procedure or training, and we have to actually, and energize work permits. So we could decrease the human factor in the arc flash incidents and reduce the risk. And we have to provide appropriate personal protective equipment, PPE. This is the final layer of the defense that we have against the arc flash. Now, the engineering controls for the arc flash mitigation includes the arc resistance switchgears. This is one type. Let's see what it is. The arc resistance switchgear is a mechanical reinforced equipment that actually contains and redirects arc flash energy away from the worker. It works like a design with a pressure relief dots at the top. The arc blast and hot gases are channeled upward. Okay, so they're not gonna direct it toward the workers and the front panel of the equipment. And doors are latched and pressure rated to basically withstand the explosive forces. Now, we could have remote operation, as we said. This is one of the engineering controls, which is basically allows the worker to interact with the energized equipment from a safe distance. We could have current limiting devices, which are the protective component that sharply restrict the peak fault current and basically interrupt the arc faster than the conventional breakers. Another one is zone selective interlocking. So it is a communication scheme between the protective relays or the breakers that allows faster fault clearance, okay, in the zone that are closest to the fault. Okay, so this is reducing that T arc that we seen in the formulas that we gone over. We could have arc flash relays that are ultra fast sensors and relays which detect the formation of an arc and trip the upstream breakers before traditional prediction relays works. Okay, so this is also a very good control strategy and design strategy for arc flash mitigation. Now, arc flash is still in the arc flash analysis and arc flash calculation is still a young kind of like engineering analysis. There are several trends that happening. We are transitioning from statistic arc flash studies to live and dynamic safety ecosystems. These trends include like a real-time arc flash dashboards, like that are linked to the SCADA system. We could have like we are developing AI enabled kind of like adaptive trip logics or augmented reality field tools. There are some work on a BIM integrated hazard overlays and intelligent PPE with sensor feedback. Okay, so arc flash engineering is not just about the calculations. Please note that it's about building the systems that prevent injuries, protect the workers, and evolve as technology advances. This is our discussion for today. Thank you for your attention. If you have any question, please let me know. Otherwise, have a great rest of the day.